Hello everyone, and thank you for tuning into my video today. I'm excited to present my final year project, which focuses on event detection for cybersecurity news articles. We'll begin with a brief overview of the background and motivations behind our research, followed by an introduction to our proposed model for event detection in cybersecurity news articles. Then, we'll discuss the experimental setup we used to evaluate our model, and present the results we obtained. Let's review the background of event detection in cybersecurity news articles. My project focuses on the application of natural language processing techniques to automatically detect event triggers in cybersecurity news articles, which is a crucial stage of event extraction. You may be wondering how a cybersecurity news article event is defined in natural language processing. An event is captured by an event nugget or trigger, along with associated arguments. A trigger is a word while a nugget is a span of text, and both indicates the occurrence of an event. For example, the phrase, "held for ransoms," is the trigger nugget for the attack ransom event in this sentence from our dataset. In addition to the trigger, an event has arguments that provide further information about the event. In this example, "computer" is an argument that supplements information about the victim, and "Colorado" is an argument that tells us where the event took place. Based on the definition of an event, event extraction involves two tasks. First, detecting the event trigger along with its type, and second, identifying its arguments. In the previous example, we detected "held for ransom" as the event nugget and classified it as an attack ransom event. We then identified "computer" as the victim argument and "Colorado" as the place of the event. In this project, we focus solely on the event detection task, which involves detecting the triggers of cybersecurity news article events. Now, let's take a closer look at the motivations behind our research. From previous research in the field of event detection, we have observed that event detection models have evolved from rule-based to machine learning to deep learning-based methods in recent years. Additionally, studies have shown that models utilizing BERT-based methods outperform those using Word2Vec embeddings. In the domain of cybersecurity, we have also noticed that there is only one publicly available corpus for cybersecurity event detection, and no prior cybersecurity event extraction shared task has been conducted. Although there are many models developed for event detection tasks, there is still a gap in the current approaches. Existing methods tend to focus on learning input text representations and using one-hot vectors for event type labels, which overlooks the importance of understanding the meaning of the type labels. However, the semantic meaning of the type labels provides key information for gaining insights into the relationship between types and trigger candidates. By presenting type labels together with the representation space of input text, we can pivot these event types. These pivoted labels can help to associate similar candidates and differentiate dissimilar ones, where similar triggers appear closer to the correct type labels and dissimilar ones appear further away from each other. Therefore, the objective of my project is to propose a neural framework that incorporates semantic type representations into the learning process to enhance cybersecurity news articles event detection. Now, let's take a look at my proposed model. As we are aware of the research gap, we have proposed a novel neural framework that exploits the semantic meaning of the type label set. Our model is called LPCNED, Label Pivoting Model for Cybersecurity News Event Detection, and it is built on the Semantic Pivoting Model for Effective Event Detection, SPEED, proposed by Huang. SPEED has three components, and LPCNED replaces the pre-trained BERT base encoder with a pre-trained news BERT encoder in the first component, where we generate unified input and label representations. Now, we look at the overall architecture of our model. In the first component, we use a news BERT encoder to generate unified input and label representations that allow for interaction between input tokens and type label semantics through attention mechanisms. In the second component, we utilize a contrastive loss function to strengthen the interaction between inputs and labels, resulting in the generation of semantic representations for the event types. The contrastive strategy is aimed at bringing together similar trigger candidates towards the pivoted type labels while also isolating dissimilar candidates from incorrect clusters. In the third component, our model employs a decoder based on conditional random fields, CRF, to generate predicted labels for input tokens. Let's now take a look at how we conduct our experiments. This is the overall flow of our experiment. To begin, we divided the CEAC dataset into 4 separate sets: training, testing, validation, and a combined training and validation set. Next, we utilized the BERT tokenizer for tokenization purposes. This allowed us to obtain both the offsets mapping and tokens. We then combined any subtokens into a single token and updated the offsets mapping for those that were combined. Ultimately, this step generated a dictionary of start and end offsets, a list of tokens, and an updated offset mapping. Following this, we used the outputs from the previous step to format the data in Maven format, the input format required for our model. This resulted in the creation of 4 JSONL files: train, test, val, and train_and_val. Finally, we conducted training and testing on the outputs generated from the previous step to obtain our F1 score, recall, and precision measurements. Now, we look at the model's performances. For comparison purposes, we used the BERT CRF model as our baseline model, which is currently considered the state-of-the-art model for event detection in a general domain. Additionally, we compared our LPCNED model to the speed model since LPCNED is an improvement upon speed. All of our experiments were conducted on the CEAC datasets testset. The results of our experiments have demonstrated that our LPCNED model outperforms the baseline BERT CRF model by 0.36% and the speed model by 0.28%. Furthermore, we conducted experiments where we varied the training data sizes and evaluated the performance of our model. Even when the training data was limited to only 20% of the total training set, LPCNED still performed robustly with an F1 score of 69.83%. This score was 1.6% higher than the performance of BERT CRF under the same percentage of training samples. Overall, this shows that our model is better equipped to identify cybersecurity events due to the type semantic representation learning and the use of the domain-specific news BERT pre-trained model, especially in scenarios where data availability is limited. Thank you for taking the time to listen to my FYP presentation. I hope that you found the information presented to be informative and valuable. If you have any questions or feedback, please do not hesitate to reach out to me.